Here we are with a momentum collision problem that we have two objects, mass 1 and mass 2, that you can see with the initial situation. We have object 1, and we should label that very clearly, being 0.5 kilograms, so this is our mass 1, and then we have a mass 2 of 0.35 kilograms, so that is our M2. Now we have information here regarding the initial velocities. Our mass 1 is travelling at 5 meters per second in the right hand direction. Our mass number 2 has initial velocity of 2.5 meters per second in the left hand direction, and that being in the opposite direction. When it comes time to our formula work, we need to consider a negative symbol to represent that. So that's something to be very mindful of. So with this problem, this is from the momentum chapter in the textbook, we have a little bit more information. So in our final situation, so after the collision, we are known the velocity and direction of mass number 2. So we are aware that mass 2 is travelling at 4 meters per second after the collision in right hand direction. So we know that both mass 1 and mass 2, they don't change their mass throughout the collision, so that remains constant before and after the collision. So the only unknown that we have, and the only thing that we need to find out, is the final velocity of object 1 and the direction of that, and we will find the direction based on the sign, either positive for right hand direction, negative for left hand direction. So let us get started. So we do know our conservation of momentum. So momentum itself is mass times velocity, but this situation is much more complex than that. We need to consider the conservation of momentum in this case. So our initial momentum is equal to our final momentum. Now our initial momentum is the addition of the momentums of mass 1 as well as mass 2. So we're going to have the addition of those on the left hand side of the equation. On the right hand side of the equation, for final momentum, we'll have the final momentum for mass 1 in addition to the final momentum of mass 2. So I'll just substitute those values in now. So to set up our equation, we have our m1 multiplied by our initial velocity 1 in addition to object 2. For our final momentum, mass 1, final velocity 1, plus mass 2, final velocity 2. I'll just highlight what it is that we are trying to find. We are trying to find this velocity 1. So we do know that both of these objects are no longer, well, they collide with each other and they are not joined. So we don't need to do any factorizing with our equations. However, the next video will show what happens when either before or after, if they're actually colliding with each other. So before I even start to substitute any values, I'd like to understand what my equation will look like. So we are trying to find this, that our velocity 1 is bound to mass 1, so it will be unwise to separate the two off the first step. So we will remove this m2 and v2 together by subtracting itself. So we'll subtract this from both sides of the equation. So we do end up with the left-hand side looking like this, subtracting our mass 2 and v2. And the right-hand side looking like this. Now the next step, I am now going to separate the mass from the velocity. It's currently being multiplied, so I will need to divide. I'm trying to find the velocity, the final velocity of object 1, so I will divide by the mass to remove it or to cancel it out. Now I'm just going to divide both sides by m1, but in doing so I'm just going to take our final velocity of object 1 over to our left hand side so we can begin trying to solve it. So that is all being divided by our mass of object 1. So if you offer a challenge, this will be a very good time to pause the video and substitute and solve yourself. Otherwise, continue watching. So I'm now going to substitute in our values, our known values that we have. So we have our mass 1 of 0.5 kilograms multiplied by our initial velocity of object 1. We're going to add that to mass 2, which is 0.35, multiplied by our initial velocity of object 2. Now, we need to consider this negative sign now because it is initial velocity, it is in the opposite direction, so I need to place a negative in front of that. That's been subtracted by mass 2, 0.35 again, multiplied by our final velocity of mass 2, which is 4. Okay, that is all being divided by our mass 1, as per our rearrangements. So we do end up getting a value for that, so therefore solving these in steps all in one go leads us to 0.45. It is a velocity, so it is meters per second. It is a vector, so we do need a direction. Now we have found ourselves with a positive value. We know that because we didn't get a negative value. So therefore we assigned our positive, we assume that to be the right hand side. So we can safely say that velocity 1 is traveling the right hand direction with a magnitude of 0.45 meters per second. So just in looking at that, let's do a little bit of a sense check. We have a larger object colliding head-on with a smaller object. That small object has absorbed most of the momentum, so a direct result of that is increased in its final velocity. So object 2 has increased in velocity between before and after, and object 1 has decreased, but is still continue traveling in that same direction. I dare say if we redid this equation and we increase this significantly, we would find a point where it would cause this larger mass to bounce in the opposite direction, and we would know that with a negative sign. But that will be a far more complex equation.